Hi guys, welcome back to my system design series, and today we are going to discuss about chapter 3 of designing data intensive applications book. So today we are going to discuss about storage and retrieval. So don't miss any of the video. This is the part 1 of chapter 3. Okay. So imagine your room looks like a complete mess. There is a missing sock somewhere, your charger is somewhere, and you are searching for your phone under the pile of your laundry clothes. It is a full chaos. But now imagine there is your room which you have perfectly organized. Everything is labeled, sorted, and easy to find. If you want your charger, then you know that you have placed it under the drawer. You don't have to hunt it. Sounds peaceful, right? Now, let's apply the same logic to our database. A database is like your room. You give it some data and it has to store in the database. And when you need the data back, you just ask the database, can you please give me my data back? Without you having to find out from different places and look for your data, it would be little bit chaos for you as well. And you want your data straightforward. So what is the trick here? How does database stays organized? Well, that is what we are diving into today's video. Alright, so you might be thinking, do I really have to take care about how database stores my data? I just need it to work, right? Well, sure, you can ignore this part, but you still need to choose the right database for your application, right? Trust me, it is like choosing between the pizza cutter and chainsaw to slice your pizza. Both are tools, but one might make a bigger chaos. Okay, so now you are not going to make the storage system from a scratch, but you will definitely need to select one out of all of this. And to do that, you need to understand how databases store and retrieve the data. So let's break it down with two classic examples. The first one is log structured storage database, and second is oriented storage database. Okay, so first, log structure storage engines. Imagine a library where you are throwing the books on the floor. So as the time goes on, the floor becomes more messy and more crowded. So one book will be on another book, it would be overwritten, and you won't be able to find out the book which is stored below. But the librarian knows exactly where the required book is kept. It is a little bit chaotic, but hey, it still works, right? Okay, so now let's talk about the page oriented storage engines. They are like the super organized library with neatly labeled, it is maths, science, English, geography, art, shelves, and categories. Everything is in perfect structure order like binary trees. Binary trees are the database version of these fancy libraries where the data is stored in the pages. They are small but neat chunks. It is like the quick index for the librarian to search the book where it is kept. So maybe to search the location of the book. Okay, so now let's take an example which would be more relatable. Imagine you are trying to search your phone from your bag. If your bag is organized, you can find your phone very easily. But if your bag is mess, just like mine, keys, gum, wrappers, or maybe a pair of sock, you will be digging it forever. And this is how your database works. A well organized storage engine like binary tree is like having your phone sitting right at the top of your bag and very easy to grab. Now back to the technical stuff. Log structured storage engine stores the data in sequential manner. Like this would be one, after that second, third, fourth, fifth. In this way, or maybe in this way, it's like stacking up the things on one table. This is fast to write, but sometimes slow to search. For example, here there are 100 books, okay, or maybe thousands of books. So you need to go in sequential order and find that particular book. So that's why it is called slow to search. But when you want to append any data, then you can just pretty easily. Put your data below or above in sequential manner. This is log structured storage engine. Now, let's talk about the page oriented storage engine. So, what it does is it breaks the data into pages. So, you can just imagine the pages in the notebook, each with the label, making easy to find it, like what you need without shuffling through a messy stack. So, the database uses this kind of pages and keeps everything nicely organized. So, it is easy to search or retrieve. So the world of database is not different from the situation which I just told you about the room, like a messy room or organized room. Whether you are using the log structured engine or page oriented engine, it is all about keeping the things tidy so you don't waste the time looking for your stuff. That is how the database store and retrieve the data without you go on and hunt your sock or find your missing mobile. Okay, so let's go a little bit deeper. Let's take an example of Bob. So once upon a time in the land of data, there lived a programmer called Bob. Bob wanted to build the simplest database using only two base functions. He didn't need any fancy tools. He just needed a way to store or retrieve the data. So he created a super simple key value store with two magic spells. So the first function is dbset and second is dbget. So dbset is to store the data into database and dbget is to retrieve the data from the database. So it took the two arguments, a key and a value, and Bob would say that dbset 1 2 3 4 5 6, and here this is the key 1 2 3 4 5 6, and the value is name, London, attractions, then this whole array. Similarly, for db set 42, 42 is the key and this is the whole value. Now this is added to the magical database file, or it looked like something like this, that 1 2 3 4 5 6 is the key and this is the value. Similarly, 42 is the key and this is the value. So if Bob want to fetch the data from the database, then it could be something like db get 42. If he writes this, then he will get the data. So this is how he could, use the key value pairs and he could store and retrieve the data. So now Bob might want to, update the data. So instead of the value in the key 42, in the attractions, the value he wanted to put instead of the Golden Gate Bridge, he wanted to put something like, for example, Exploratorium. Okay. Now the database would look something like this. Database set 42 holds as it is, but instead of Golden Gate Bridge, it would be Exploratorium. Now Bob wanted to update the data. So in the DB set 42, here in the value attraction, instead of Golden Gate he wanted to add Exploratorium. So as he wanted to update this particular data, he added a new line and it looks something like 1 2 3 4 5 6, the same one. This is also same, this is also same, but here the keys 42 are same but the value is different. You can just see. Now it will create the ambiguity. So this is how it is stored. And now if the Bob want to fetch the data on the key value 42, he will fetch this last data, which is the latest one. So this is all well until Bob's database gets increased in size. One day it becomes so large that it would become very slow to fetch the data and to find the latest value of the key. And dbget have to scan the whole entire file every time. And the cost of searching was like walking through the giant big library, one book at a time. And for every new book, the search got longer and longer. Bob realized this problem, and here the search time is O of n. And the more data you have, the slower the search of that particular book will be. And so Bob decided to find a solution called index. Okay, so let's talk about the index. And Bob's index was like a magical map for its database. So instead of scanning whole library, he could use this particular map to instantly find the book. So an index is the essentially extra metadata that helps you to quickly locate the data. But here is the thing. Creating the whole map or an index is takes effort. So imagine the Bob have lots of books in his whole library. So instead of searching the books one by one, Bob creates a separate list of book titles so he can jump straight to the book which he wanted. And this map is great thing to find these books very easily and quickly. But if the Bob will create this kind of maps more, it would be very difficult to maintain them, especially when you are adding the new book. So if Bob wanted to add a new book, he can just throw on this particular library. So he can just throw the book 6b6 on the library. He can just throw it on the shelf. It is like appending to a file, which is super fast. But if he wanted to make or maintain the index or map, he have to update every time this whole map when the book is added or there are any changes in the place of a book, and this will make the adding a book a little bit slower. So here is the catch: indexes speed ups read operation but slowest write operation. So, without the index, Bob's library is easy to add the books, but searching is slow. And with index, searching becomes very fast, but adding the books requires updating the index, which takes the extra time. So, because of these, Bob realized that he had to learn about the different types of indexes, and some are better for some searches while others are better for some other use cases. So here are some of the types of the indexes which Bob learned about. So first is hash index. It is like a super fast catalog where each book is assigned a specific number. For example, find a book by its title. Second is a balanced tree structure, like a sorted list of book titles that helps to find the books quickly. So it is used when you want to perform the range query. Suppose find the books between 30 and 40. So here just imagine it is 30 and this is 50, this is 40. So you will be able to find the books which are kept in between 30 and 40. Third is log structure merge tree, a clever index used in the modern databases. It keeps the data in the sorted files and then merges over time. It is like organizing the books into categories and later merging them into the one giant collection. So let's talk about the moral of Bob's adventure. Shortcuts to find your data quickly, but they come at a cost. They slow down the writes because they needs to be updated every time new data is added or changed. Just like in real life, when you choose an index, you need to think about the trade-off between how often you need to read the data and how often you need to write the data. And the best solution depends on your needs. Okay, so let's talk about the indexes. Imagine you walk into the Hashland to find your favorite book called The Archies. Now you know the title, but how will you find this among millions of books? The solution is hash map. A hash map is like kind of magical catalog that helps us to instantly locate any book using its title or key. So each key is linked with the unique location called byte offset in the storage system. Think of it as a magical card catalog that tells you the exact shelf number where your book is kept. So now let's talk about the how hash indexing works. First is the magic of hashing. When we store the data, suppose the book, the Archies, we use the hash function to compute the unique location for it. This way, we don't need to go to wild goose chase through the entire library. The hash map directs us straight to the correct shelf. For example, this is the library, and these are suppose six shelves: S1, S2, S3, S4, S5, S6. So suppose the book's title is The Archies, and here taking the title, the hash function is created, and it suppose says that, but instead of S1 and S2, S4, S6, the naming convention would be something like 121 123 125 201 1005 1009. So it will create the hash function and the arches will be converted into 1 to 5 for example. So this book will be stored into the 1 to 5 place or location. Second is it is simple and fast. So once we store the data, the hash map keeps the track of it and it is quick to find. The hash map lives into the library's brain, that is a RAM. So it is super fast and the data itself can be very massive and lives on the bookshelves, that is the disk. But don't worry, the hash map makes sure that we don't spend a lot of time in searching. Now, here is the catch. If we have lots of books, that is, we have lots of keys, the catalog, the hash map becomes too much big for library's brain, that is a RAM. So, this is a problem when the books number of books grows exponentially. But that's where Bitcask comes into the picture. So, what is the Bitcask? It's a kind of librarian who keeps the things running smoothly in the library by ensuring we don't lose our way and the library doesn't run out of the space. So, instead of rewriting books or replacing the old data, Bitcask uses a clever idea where new entries are appended to the end of the storage file. So let's take an example of this particular YouTube video and we are making a count of how many times this video has been played or watched. So instead of updating the old video, we simply append a new record at the end of the file. So for example, this is the YouTube video. Suppose system design video 1 and suppose it is played 2 times as of now. After that, there is another system design video, it is system design second video, and it is played 7 times. Now, after some time, this first video has been watched multiple times and its count increases. So instead of updating this particular number, we are appending a new record as system design 1 as suppose 2. Instead of 2, we will write 3. So here we are appending the updated count instead of updating the record. It is like adding the new pages without erasing the old ones. So the record is never overwritten but always appended with a new play count. So each change gets its own fresh new entry. So this we talked about the append one, append only, and now let's talk about memory map. So as the play count gets updated, Bitcast uses the hash map in a memory to track the new record's location. Okay, yeah, here it is. So whenever you want to check that how many times the system design one video is being played or second video is being played, then use the hash map. Now let's talk about the compaction. A Bitcast has a special power, a cleanup spell called compaction. So over time, the library gets updated or system design videos count will get updated. So this whole thing will get bigger and bigger. And we might end up having the many versions of the same particular video or a book. Maybe the system design one video is been updated 1,000 times. So to keep the things neat, Beatcast uses the compaction, which means it keeps only recent version of the videos or books and throws the old ones. Okay, so let's understand that suppose we have system design one video, system design two video, system design one video, system design one video. First, we've got two views, got five view, seven, and 1,000. Now, after compaction, we will remove the SD1, 7 and 2 and we will keep the recent version. And after that, we will merge these two ones, that is SD2 having the 5 and SD1 having the 1,000. So, this merge file is the cleaner, smaller and much more efficient. So, the old records are compacted away and the new files are easier to navigate. So, this keeps the whole storage block organized and prevents the disk blown, ensuring the library doesn't get overwhelmed by too many old books. Okay, so let's talk about some special features of Bitcask. First is deleting records. If the system design one video gets deleted, we just don't erase it. Instead, we just add a special tombstone record to the log, indicating that the key is no longer available. And during the compaction, the tombstone ensures the older data gets discarded properly. Second is crash recovery. If the library crashes in middle of writing a new record, for example, if the count of that particular system design one video changes, so in the mid write, Bitcast ensures that we don't end up half written books. The checksum helps to detect the corrupted parts, and Bitcast's clever system ensures that the latest version is kept. Third is concurrency. Multiple library assistants or YouTube videos assistants will work together called threads to serve your request, where one assistant is writing the new play count while another is serving your request to find the recent play count. So Bitcast makes sure that there is no concurrence between these two operations, so everything runs smoothly. While Bitcast is a powerful librarian, it do have the limitations. First is memory limits. The hash map must fit into the memory. If there are too many books, for example, keys, we will run out of the library's brain. That is a RAM space. And second is no range queries. If you want to scan the all the videos between system design 1 to system design suppose 20, you will be disappointed. Hash indexes are not great for range queries because they are designed for a quick lookups and not a sequential scans. So why to use hash indexes or bit cache? So despite of these limitations, it is the most powerful combination. First is it have the fast writes whenever it's needed, as the play count of the system design video continuously changing, so we need the system to handle this change very smoothly. Second is frequent updates. So here we update the same key. For example, the number of views of particular one video often changes. And Bitcask handles this particular situation by appending the data and keeping the latest update. So third is efficient storage. By using the compaction and segment merging, Bitcask makes sure the storage doesn't get blocked or get inefficient over time. So let's sum up. Hash indexes. These are the quick and efficient in-memory maps that directs us to data on disk, helping us to avoid wild goose chase for our key value pairs. And second is Bitcask, a magical system that appends the updates, compacts the old data, and ensures that everything stays organized and efficient, making sure that we can handle the data like system design video with speed and precision. So a magical combination of both of this creates the high performance, write heavy system that keeps the data accessible and storage is optimized. And please make sure you like this video, subscribe to my channel and leave the comments if you have any kind of doubts or suggestions or you want any particular topic so that I can make the video on that. Check out the descriptions if you want the more resources supporting the information which I have explained, and see you in the next video.